Welcome to Omni Eyes channel. Today we will explore the incredible sensory world of the cricket and its biological radar system. This tiny insect holds profound secrets about advanced surveillance technology. It is a master of blending different sensory inputs for survival. In the deep shadows of the forest, the cricket relies on more than just its vision to detect any approaching dangers. While human engineers struggle with complex sensor integration, this humble creature has perfected the ultimate audio-visual fusion over countless generations. Let us look closer at the amazing anatomy of this insect. The journey begins with its large and specialized compound eyes. These unique eyes are perfectly designed for rapid motion scanning. They can detect the slightest movement in their immediate surrounding environment. Imagine having thousands of tiny lenses working together simultaneously. This provides the cricket with a wide and comprehensive field of view. However, vision alone is never enough in the unpredictable wild. A clever predator might approach silently from a blind optical angle. This is where the second layer of defense activates. The insect possesses an extraordinary biological radar built right into its body. Tiny sensory hairs located on their legs act as sensitive vibration detectors. They can feel the faintest tremors in the ground. When a predator takes a step, the impact sends shockwaves through the earth. The cricket feels this long before seeing anything. These specialized vibration sensors are incredibly precise. They can determine the exact direction and the intensity of the approaching physical threat. Now, we reach the most fascinating part of this biological marvel. The cricket does not use these two distinct senses independently. Instead, its tiny but powerful brain performs a complex operation. It merges visual data with physical vibration data in real time. This sophisticated process is known as audio-visual fusion. It is the ultimate key to the survival rate of this species. If the eyes see a moving shadow, the brain waits. It checks the leg sensors for any matching ground vibration signals. If there is no vibration, the brain ignores the visual movement. It assumes the shadow was merely a harmless falling leaf. Conversely, if the legs feel a sudden, strong vibration without any visual confirmation, the cricket remains still to avoid unnecessary exposure. But when both the visual motion and the ground vibration happen simultaneously, the system triggers a very urgent biological alarm signal. This dual confirmation mechanism is brilliant. It ensures that the cricket only expends its valuable energy when a real threat exists. False alarms are a massive waste of resources in nature. Running away from a falling leaf could accidentally expose them completely. By demanding matching data from two entirely different sensory channels, the insect achieves flawless threat detection accuracy in a chaotic environment. Modern human engineers have recently started copying this exact biological strategy. We call it layered surveillance, or multimodal sensor technology. In the past, security systems relied heavily on a single data source. A simple motion detection camera was often considered enough. However, single sensor systems are notoriously prone to annoying false alarms. A heavy gust of wind can easily trigger a camera. A stray dog walking by, or a branch moving in the storm, could cause a traditional security system to sound alarms. To solve this frustrating problem, engineers look directly at the cricket. They realize that true intelligence requires multiple layers of verification. Today, a state-of-the-art perimeter defense system uses multiple tools. It combines high-definition optical cameras with seismic sensors. The optical camera acts exactly like the compound eyes of the insect. It constantly scans the perimeter for any suspicious movement. Meanwhile, the buried seismic sensors act like the sensitive leg hairs. They listen carefully for the heavy footsteps of an intruder. When the camera detects a moving shape in the dark, the central computer does not immediately trigger the loud security alarm. Instead, the intelligent software queries the ground sensors. It asks if there is a corresponding physical footprint matching that visual location. If the ground sensors report absolute silence, the system understands the truth. The moving shape is likely just a harmless artifact. It could be a shadow cast by passing car headlights. It might simply be a large bush blowing violently in wind. Because the two data streams do not match, the system remains calm. The false alarm is successfully suppressed by the algorithm. But if the camera sees a human figure and the ground sensors feel heavy footsteps, the system recognizes a security breach. Only then does the system activate the final security protocols. It alerts the human guards and turns on the floodlight. This layered approach drastically reduces the operational fatigue of security personnel. They no longer have to respond to thousands of alerts, The cricket taught us that a truly smart system never relies on a single source of information to make critical decisions. Redundancy and cross-verification are the foundational pillars of reliability. Nature figured this out millions of years before humans existed here. Let us dive deeper into the microscopic world of the cricket eye. Each individual lens captures a tiny fragment of environment. These fragments are stitched together in the brain. The resulting image is not high resolution, but it is sensitive to changes. This low resolution but high-speed visual processing is highly efficient. It requires very little brain power while maximizing reaction speed. Human computer vision systems are now adopting similar efficient processing methods. They focus on detecting changes rather than rendering static images. This technique is called event-based vision. It is directly inspired by the biological eyes of insects like the green cricket. By processing only the moving parts of a scene, artificial intelligence can react much faster and use significantly less computing power. Now consider the physical design of the vibration sensors. The tiny hairs on the cricket legs are tuned to specific frequencies. They filter out the background noise of the busy forest. They only respond to the specific rhythmic thumping of a predator. This mechanical filtering is another brilliant lesson for human engineers. We often struggle to separate valuable signal data from background noise. By designing physical sensors that naturally ignore irrelevant data, we can save massive amounts of digital processing power in security systems. The integration of these two optimized sensory streams is a masterpiece. It represents the pinnacle of natural evolutionary engineering survival strategy. When a hungry bird swoops down from the sky, the air pressure changes. The visual field shifts rapidly as shadows fall. The cricket processes both the visual shift and the subtle air vibration. In a fraction of a millisecond, it executes escape. A powerful leap propels the insect to absolute safety. The predator is left grabbing nothing but empty dirt and dry leaves. This lightning-fast reaction is only possible because the sensory fusion happens subconsciously. The brain does not waste time pondering data. In our artificial systems, we call this edge computing. The data is processed locally at the sensor level to minimize delays. A smart camera does not send all its raw video footage to a distant cloud server for heavy and slow processing. Instead, it analyzes the motion locally and only sends a tiny alert signal. This mimics the highly efficient insect neural pathways. The synergy between the visual and tactile domains is truly extraordinary. It creates a comprehensive situational awareness that is extremely reliable. Imagine a future where autonomous vehicles use this exact same logic. A self-driving car cannot rely solely on optical cameras. Bright sunlight can blind a camera lens completely. Heavy rain or thick fog can obscure the visual data required for driving. By integrating laser radar and physical acoustic sensors, the car creates a layered perception system. It becomes resilient, like the cricket. If the camera is blinded by the sun, the radar still detects the vehicle ahead. The fusion system prevents a collision. The principles of audio-visual fusion are universally applicable. They extend far beyond simple security cameras and enter the robotics realm. Advanced robots are now being equipped with tactile skin sensors. These sensors work in perfect harmony with artificial stereo vision cameras. When a robot reaches out to grab a fragile object, its eyes guide the initial movement. But tactile sensors take over. The skin feels the exact pressure required to hold the object without crushing it. This is multi-sensory integration in motion. Just like the cricket navigating the complex forest floor, the robot uses multiple data streams to interact safely with the world. Every time we study these small creatures, we uncover profound engineering wisdom. Nature is the ultimate research laboratory for human innovation. Millions of years of rigorous evolutionary testing have eliminated all inefficient designs. Only the most robust and intelligent biological systems remain. We must learn to observe these natural mechanisms with great humility. The solutions to our most complex technological problems are here. The cricket does not need a massive computer. It achieves perfect situational awareness with a brain the size of a pinhead. This extreme efficiency is the holy grail of modern artificial intelligence. We strive to build algorithms that do more with less. By studying the neural architecture of the cricket, scientists are developing novel neuromorphic computer chips, mimicking these biological neural sensory networks. These advanced chips can process visual and auditory signals simultaneously. They use a fraction of the energy required by traditional processors. The future of smart devices lies in this biological inspiration. Our smartphones will soon have layered sensors that understand our context. Your phone might use its camera to see your face, while its microphone listens for your voice to confirm your identity. This dual authentication process is exactly what the Cricket does when verifying a threat. It is a foolproof method establishing truth. Let us return to the dark forest where our story began. The Cricket sits quietly on a wide leaf, constantly vigilant. Its compound eyes scan the moonlight shadows for any sudden movement. Its sensitive legs monitor the subtle vibrations of the branch. A large predatory spider approaches slowly from behind. The spider is incredibly stealthy, trying desperately to avoid making any loud noise. However, the spider cannot completely eliminate the microscopic vibrations of its footsteps. The sensitive leg hairs of the Cricket detect danger. The visual field is clear, but the tactile warning is overwhelmingly strong. The fusion center in the brain makes a decision. The Cricket jumps away into the safety of the dark undergrowth. The hungry spider is left behind, completely baffled by escape. This daily drama of life and death is dictated by sensory perfection. The audio-visual fusion system worked flawlessly once again. As we build our own smart cities and intelligent security networks, we must always remember the valuable lessons taught by insects. A single sensor is a single point of failure. It is easily deceived by environmental noise, clever camouflage, or mechanical malfunction. A truly intelligent network requires diverse inputs. It needs eyes to see the light and specialized tactile sensors to feel vibrations. When these diverse data streams converge and agree, we can act with absolute confidence. We can completely eliminate all false alarms. The beauty of nature is not just in its visual splendor. It is found deeply embedded in flawless, logical engineering systems. Every creature is a masterclass in survival optimization. We just need to pay close attention and decode their hidden operational secrets. The humble Cricket is a perfect example of this hidden genius. It is a living blueprint for the future of technology. From the dense jungle floor to the highly secure perimeter of a modern data center, the fundamental rules of surveillance remain. You must look, you must listen, and you must feel. Only by combining all these senses can you truly understand reality. The integration of multiple perspectives creates a robust reality. This is the profound truth embedded in the concept of sensory fusion. We hope you have enjoyed this fascinating journey into the microscopic world. The natural world is full of incredible technological marvels. Next time you hear a cricket chirping in the warm night, remember the sophisticated biological radar system operating inside its body. It is not just a simple noisy bug. It is a highly advanced sensory machine, perfectly adapted to a dangerous world. By embracing the wisdom of biology, human engineers will continue to create smarter, safer, and much more efficient systems for everyone. The gap between biological evolution and human engineering is closing rapidly. We are finally learning how to replicate ancient natural designs. Thank you for joining us on this exploration of multisensory integration. We are dedicated to bringing you the best science. If you found this biological analysis intriguing, please consider subscribing to our channel. We have many more amazing natural engineering secrets. Share this video with your friends who love science and technology. Let us spread the profound knowledge of nature to everyone. Stay curious, keep exploring, and never stop questioning the wonderful world around you. The universe is full of endless mysteries waiting. This concludes our episode. Thank you for watching Omni Eyes channel. We will see you next time for another scientific adventure.